Hello everyone, this is Mr. Tickner and this is your first video in the astrophysics topic. We're going to make these to go through these little mini units. So today in this video we're going to go through this, and I'm going to get the right pen. We're going to go through motion in the universe. Okay, so a lot of this first bit is actually quite straightforward stuff that hopefully you'd be fairly able to be aware of even without this. So we need to know something about what is the universe made of. Okay, so we need to know these terms of the universe, galaxies, stars, and the solar system, and having a basic understanding of where things are. So let's take you on a very brief little tour. You are currently here. You are inside the solar system. You are on this third planet, okay, third rock from the sun. We're on the Earth. There are lots of planets. There's some dwarf planets. You don't need to know the differences between them. And you're orbiting the sun. Okay. And the sun is in this thing. This is the Milky Way. There is no picture of us outside the Milky Way because we've not really gone out of it. I mean, the bit of the Milky Way that you can see with the naked eye of actual individual stars is a sort of a tiny amount. You can kind of see this sort of, you can see something around there. You're about there. You can just about, if you've got good eyesight, make out the galactic core, but you can't see individual stars. You just see, a streak across the sky, which has led to the name the Milky Way. Milky Way is really big. It's 100,000 light years across. Okay, so we're about 30,000 light years from the middle. Okay, so this distance here is about that's 30,000 light years. That means that basically, if you were to try and phone someone, it would take 30,000 years for that message to get to someone who's there. The whole Milky Way is 100,000 light years. So communicating across, even at the speed of light, communicating around the galaxy is would be a very slow process. Okay, so there are around about 250 billion stars to maybe 1 trillion stars in the Milky Way. Okay, it's a large number. Okay, obviously we haven't been outside the galaxy, so here's the nearest neighbor. This is Andromeda. Okay, so this is what we think. Basically, if you were outside the Milky Way, this is what it would look like. Andromeda is a very, very long distance away. It's 2 million light years away, so it's a very, very big distance. But this is what a galaxy looks like. It's a big swirly thing with a large number of stars in the middle, small and dust lanes and stuff. It's a really majestic image. Down here, this is called a dwarf galaxy. So galaxies can be small, like this one, or they can be really big. Okay, us and Andromeda, we're the two big galaxies in our area, and then there's little dwarf ones that are orbiting around them. How many galaxies are there? It's quite a lot. Most of the things you can see. This is the Hubble Ultra Deep Field. This is pretty much everything in this, with a few exceptions. These are all galaxies, all these dots here. So that's a galaxy, that's a galaxy, that's a galaxy, that's a galaxy, 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 galaxy. You can kind of get the idea. Every single one of these dots, these are all galaxies, except for that one. That's a star, and that's a star. Star, but galaxy, 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 galaxy. So this is just a small patch of the night sky, and they took it because there aren't many stars visible in it, and it turns out that beyond them, even this one here, there's all these galaxies. Okay, this is when we talk about there being billions of galaxies, there really are. What this would look like in terms of how much of the world around you this take up. If you took one of those pieces of graph paper that you love so much, okay, the sort of like piece of graph paper and all the things, and everyone goes, my eyes, I can't see them. The square in a graph paper, okay, these are, I think they're 2 millimeter size pieces of graph paper. So the little tiny squares that hurt your eyes are 2 millimeters by 2 millimeters. That's how big they are. This image, okay, 4 of these images would fit in one of those squares if that piece of graph paper was held at a meter away from you. So this is a tiny fraction of the sky, of everything, and just look how many galaxies there are. Okay, so there are just a ridiculous number of them, each of them holding billions of stars. So what essentially, I mean, there's not a lot to know. You just need to know sort of this. Okay, there's not really much a nicer way to write it. Know that the universe is made of billions of galaxies. Large. It's enormous. Okay, collection of billions of galaxies. A galaxy is a collection of billions of stars, and our solar system is what we call the Milky Way galaxy. So that's home. So those are the sort of terms you need to know, sort of multi-choices. Right, second bit. Understand why gravitational field strength G varies and know that's different on other planets and the moon and that on Earth. You don't need to know values. You don't need to know anything other than the fact of, okay, they change. Now, if we think about our image here, okay, the key equation that sort of, when we're linking when with that is W equals mg. Okay, so the force of gravity you feel somewhere is about how much mass you have multiplied by the gravitational field strength in your local area. Okay, so on the Earth, if you stand on the Earth, it's 10. If you stand on the surface of Jupiter, it's about 25. If you stand on the surface of the Sun for some stupid reason, it's about 250. If you stand on Venus, it's about 8. If you stand on the Moon, which you can't see, it's about 3.4. So different places. And what is different about all these things? Okay, if you are standing somewhere on a planet or a moon or anything, okay, the value of G will change due to the mass and the size. Okay, so in size in terms of how big it is and how much stuff is there. So sort of radius, if you want to be there, because they're spheres. The mass or the radius, so the mass and radius of the planet or moon. So whatever object you are currently standing on. Okay, if you disappear off into space, so you're off to here, then yes, gravity, you go further away from things. That does affect it as well. But if you're this is always about if you're standing on a planet or on a moon. You don't need to know any of these values. Even the Earth is a value that you're given, so you might be asked to work it out, or you might be asked, or you might just be given it as part of the question. But that's that's the thing that changes. G is essentially a thing that kind of can give you an idea about what's in your local area and where you're standing. Right, this force, this gravitational force, what does it cause things to do? It causes moons to orbit planets, planets to orbit the sun, artificial satellites to orbit the Earth, and comets to orbit the sun. So there are these little things you need to know about. Okay, so let's take them. What are moons? Well, here's ours. Okay, this is the moon. Okay, and lots of planets, they will have moons. So I think I've got an image of Saturn down here somewhere. Yeah, there we go. Here's an image of Saturn. There's the moon Titan. I think that's Titan. But there's another moon there, and there's a moon there. So Saturn has lots of moons. It's got about 40 odd. Jupiter's got about 60. Moons are natural things. Okay, so they are. So if it's a moon, it means it's a natural thing that's orbiting a planet. Okay, and they'll orbit the planets because they're smaller. Okay, they are physically smaller than the planet orbiting. Satellites are man-made. This is Sputnik, or a replica of Sputnik, which was sent up in 1957. And we can send them into any orbits we want and around anything we want because we're in control of them. And then we have comets, this is Comet Hale-Bopp, okay, and taken in 1997. And basically they are dirty snowballs that are orbiting the sun. So essentially what we have are, think of our sort of things, we have planets, they orbit the sun. We have moons, they orbit planets. We have satellites, we can put them in orbit around anything. And we have comets that orbit the sun. So this gives us a nice sort of diagram which helps us with number information. So they're things you might need to recognize just as terms because they get used. Describe the differences in the orbits of comets, moons, and planets. So I always think of this as terms of orbit shapes. So the way to think about this is a very, very, very simple solar system. So we're going to think about a star. Okay, that's the big star, and because it's very massive and it's got very, very dense, it causes things to orbit it. So we're going to have a planet, and let's have a planet that's here. that planet is probably a bit too big. So you know what? Let's make our star even bigger. There we go. You're not going to be as big as me. Okay, so there's our star, S. We've got our planet, P. And our planet goes around the star in basically a circle. You might be aware that it's not a perfect circle, but the calculations that we're going to do, it's going to go round in a circle. So planets, planets orbit stars in circles. Okay, so we're going to have a circle. And what's nice, we'll come to this later, but the defining thing of a circle is a radius of the orbit, which is R. We'll think about that in a moment. Moons. So I'm going to put a moon. I'm going to put moon here. Moons orbit planets, and again, we're going to try and see if I can draw a perfect one, and I can't. But we've got, again, we have moons, so I'm going to call that M. So we've got moons orbit planets in circles. Okay, so we've got circles and circles. The final thing are the comets. Comets, they orbit in a thing called an ellipse or an oval. So they will come in from very, very, very far away. They swing in, they swing around the star. They go off into the far parts of the solar system. Okay. When they have their big tails and stuff, they are kind of close to the sun. Okay, and if they are very far away, they don't. So let's move this over here. So comets orbit in ellipses, which is otherwise known as an oval. Okay. Again, they're orbiting the star. Okay. And it's a bit like a roller coaster. They fall in and then they zoom out again, and there's still that conversion of gravitational and kinetic energy. So when they're out here, they are moving slow, and when they're here, they're moving fast. So they have a changing speed. If they're close in, they're falling in, and that's basically the shapes that you need to know. Circles around stars, circles around planets, and ellipses or ovals around stars. So sometimes you're just given a kind of a diagram like this, and you have to label it with which one's the planet, which one's the comet, which one's the moon, which one's the star. Okay, so do that. Right, so we've done that. We've done all that. We've done that. We've done that. So the last thing is the mathsy bit, the bit where we have to work something out, and that's this bit here. Use this relationship. So it's a relationship you are given. Of course, you are given all of them, between orbital speed, orbital radius, and time period. Okay, so if we think about this, we're basically using the equation speed is distance over time. We have a planet, it is going around in a circle. Okay, so it's going to go a distance. Let's go back to green so that we're consistent here. So, so the planet speed, okay, is equal to distance over time, which is basically we've got the circle with a length of 2 pi r, so that is the circumference of the orbit, which I think I may have spelled circumference wrong, over the time for one orbit. So when they say time period, it's how long does it take. That there is time for one orbit, and 2 pi times radius is the length of one orbit. Okay, so this is a thing that we get. So what we can do is let's do a little bit of an example, and let's do the speed of the Earth. Okay, so I'm going to do 2 little quick examples using a couple of real things. So let's work out the speed of the Earth. Okay, so the speed of the Earth we need to know a few things. We need to know the orbital distance between the Sun and the Earth is a big number. It's 150 million kilometers. And the time for one orbit is 1 year. Okay, and now let's think. We can pick different units. Let's go with kilometers per second, partly because I know the number I'm looking for, and also it's a nice one to actually try and work out. So orbital distance, here's the thing. So let's think, okay, so how long is 1 year in seconds? Okay, so 1 year equals 365 days. I'm ignoring the quarter. Okay, so we have to be times by 365 to get into days. Days, okay, well, that's going to equal 365 times 24. If I multiply that by that, I would get the number of hours. Okay. If I want to go into minutes, I have to multiply by 60. So I have to go 365 times 24 for the number of hours times 60 minutes. And then I want to go to seconds, so I have to multiply in, so 365 times 24 times 60 times 60 seconds. Okay, this is going to be a big number. Okay, and I've got my trusty calculator because it is a number that I, going to be interested to see what I get. So I've got 365 times 24 times 60 times 60, and I get a biggish number. I get 31,536,000 seconds. Okay. The difficulty with this is that you end up with large numbers. Okay, there's not a lot you can do to avoid it. This is how many seconds it is. Sometimes they might say, "Oh, do it in hours or do it in, days or whatever." But we've picked seconds because I'm a fool. So that's our time. Okay, then we have to say, right, okay, our distance of the orbit that we're the orbital distance. Our distance from the Sun is 150 million kilometers. So therefore, we get our circumference. I've not written that and using the best way. I was a bit lazy there. I have to then multiply that by 2 pi. Okay, so this is how far we are from the Sun. That's the radius times by 2 pi to turn it into something. Times by 2 pi to turn it into circumference. So let's do that. We get 150. 1, 2, 3, 4, 5, 6 times 2 times. I'm just going to use 3.14 because I'm lazy, and I get about 942. 1, 2, 3, 4, 5, 6. 942 million kilometers. Okay, so my speed is this number divided by this number. So I do speed is equal to 942, 1, 2, 3, 4, 5, 6 over 31,536,000. And I get 29.9. What's my unit? I was in kilometers and in seconds, so I'm 29.9 kilometers per second, which means that every single second that you sit on the Earth, every one of these clicks, you are moving 30 kilometers around the Sun. That is the distance from wherever you are, probably to South London. Okay, 30 kilometers, fairly big distance every single second. So that's how you can do the speed of the Earth. Let's do a slightly different one. Let's deal with Saturn and its various moons. So let's think about I want to know the orbit time of Saturn. Okay, so they might ask you to rearrange things a little bit. Still dealing with horrible numbers, but you've got to say that. So the information we'll start with here is I'm going to give you the radius of the orbit. It's 10 times further away than it is from the Earth. So it's 1,500 million kilometers. So Saturn is 10 times further away from the Earth than the Sun is. Speed of orbit, I'm going to give you v, and it's going at about 10 kilometers per second, roughly. Okay. So what I want to know is the time of an orbit, and let's see about getting it into years. Okay. So let's look at our equation. Okay, so we're going to have between speed is equal to 2 times pi times r over t. So we can put our numbers in. We've got 10, okay, kilometers per second is equal to 2 times pi times 1,500,000 over t. And if we do this, we're going to get it in seconds, okay, because this is in kilometers per second and this is still in this will give in seconds. So we've got, that's why we picked 10. It's quite a nice number. So we get 2 times pi times 1,500,000. So many zeros over 10. That's nice. We can cancel that out. So we've got 2 times pi times 150 million. Okay. So let's actually just do that multiplication, and we'll end up with a number, and then it'll be in seconds. So we've got 2.14 times 1,500,000, and I've got it's the same. So I've got 942 million seconds. If I want to turn that into minutes, okay, I'm going to divide by 60. So if I divide by 60, I get 15,700,000 minutes. I'm going to divide by 60 again to get it into hours. And I'm going to get there, I get 261,666 recurring, so 67 hours. I want to get that into days, so let's divide by 24. I have now got 10,902, so I'm just going to round that to about 10,902 days. Approximately how many years is that? Well, let's divide by 365. Again, I'm ignoring the quarter because I don't care that much. 365, I get 29.9 years, or around about 30 years. So if I lived on Saturn, I would be 1 1/3, because I would have only gone around the sun once. So that's the mathsy bit of this part. There's obviously a lot of, it does involve some difficult numbers, but if you take it through step by step, they'll often help you by giving you, for example, the number of seconds in a year, or they'll deal with it in kilometers per day. So just make sure you watch out for the units they're using. And yeah, that is what you need to know about this first topic, and I'll see you for the next video.